Hello, everyone, and welcome to today's SANS webcast, Hacking the Security Footprint of Open Source Dependencies, sponsored by Snyk. My name is Carol Auth of SANS, and I will be moderating today's webcast. Today's featured speaker is Liran, developer advocate at Snyk. If during the webcast you have any questions for our presenter, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to turn the webcast over to Liran.
Hey everyone, my name is Liran. Thank you for joining me. It looks like we're starting off, so I'll go ahead and introduce myself. I'm a developer advocate at Snyk. I'm here to talk to you today about security and how it impacts open source, from dependencies in application languages to containers, and we'll even see real-life examples of that. So I'm from Israel. As I said, I'm a developer advocate at Snyk, where we build developer-friendly security tools to help empower developers find and fix open source security in their projects. I'm also actively involved in other security communities, like the Node Security Working Group, kind of like helping improve the state of nodes and the NPM ecosystem in that sense. OWASP and all of those. So if you want to ask anything, if you want to reach out, of course, I'm on Twitter, Liran_tal. And if you have a lot of questions for me afterwards, I'd be happy to go through them. So indeed, don't forget to leave them on the chat box with a question. So with that said, let's start. So, open source is awesome. This is going to be an amazing start to open this presentation. We're all using open source. Some of us may be even contributing back. Some of us may be even maintaining some popular and great packages and projects for the ecosystem. We're all citizens of open source, and this is awesome. What also is awesome? Icebergs. Icebergs are also awesome, and they have two things in common. The thing is that there's a lot of a backend there with icebergs, right? You can see just the tip of it, but there's a lot going on behind the scenes if you look a bit, deeply into it. And so this is, starting straight off with an example of what we'll be talking into. Have this, 19 lines of code Lambda function, which I've deployed onto the cloud. And it's a very simple thing. What it does is fetch a file, store it, on the cloud. And it uses two dependencies to do this. So this is an NPM-based, JavaScript-based Lambda, uses AWS SDK and Node Fetch. So all of those, only those two dependencies, except the real impact of these 19 lines of code and two dependencies is actually more around the 200,000 lines of code that are my entire surface of code and IP, and everything that helps me power this Lambda to function properly the way it should. And that is where things, get a bit messy and hairy, and we need to be a bit more careful and understand what's going on there. So, bringing this into like our opening, introduction here today, I think nobody is going to question the fact that open source software has made an incredible impact on modern software development, and it continues to expand every year. As a testament of that, you can see the growth around ecosystems happening in open source registries. One obvious example stands out very clearly here, and on Twitter debates, Reddit, and whatnot. Devs to devs kind of talking between themselves. NPM, right? NPM as an ecosystem spanning over 1 million packages, 1.4 to be exact. So this is a testament of open source packages and growth and how we're using them day to day. JavaScript specifically taking more load from the browser, and different kind of aspects of day-to-day software development. But the thing is, how much do we really know about our dependencies? How much do we really know about the maintainers who build software with them? How much do we really know about all of those packages that we add in? Were they security tested, vetted? What was going on there? And the thing is, we probably don't know too much about what is going on there. And I'm here to kind of like give you a bit of some kind of also a 360 view of what's going on there. And so to do that, even to educate myself, what I do is I read a lot of academic research papers. One of which is this one, which I captured a few highlights I want to share. And so this one particularly tried to look at the difference, or rather maybe see what it can find, whether those are differences or similarities between two different ecosystems. One is NPM JavaScript, and the other one is PyPI, which powers Python. So as it looks into them, and I'm going to focus on the NPM parts here, as these are the more interesting highlights here. It concluded, one of the findings was that 61% of all packages on NPM could be considered abandoned. And the thing is, what makes a package abandoned? What drives it into that kind of criteria? And so what happens is, for this research paper, the authors have decided that the criteria for an abandoned package would be any package that did not have a release in the last 12 months, or the last year, effectively. If it did not have it, it would be considered as an abandoned package. Granted, this being that you may contradict this or counter-argument this with saying perhaps the package is mature, perhaps the package has reached a stable state, there's no more bug fixes, this is just ready to go. Except that's probably not going to be the majority of cases. One of which we've seen an incident for a package that would have been classified as into that criteria of an abandoned package as one of those 61%, is event stream, and the event stream incident, security incident that happened just a couple of years back. So let's quickly take a look at what is going on. There's an entire postmortem that's super interesting to read if you're into this and haven't heard about this, as this has been something super major, but just going through this pretty quickly. This was a package that was owned by a person called Dominic Tarr, a very friendly and productive developer and maintainer of an open source ecosystem, specifically on NPM. So he created event stream that existed on the NPM registry since 2011, and particularly didn't really receive any new releases in the last 2 years, therefore could be considered one of those 61% packages of abandoned packages. But suddenly, a person shows up on GitHub as a repository of that package, opening an issue for their own dependency and wanting to help. And so they further contribute several PRs, try to add more features, try to fix things, and then kind of like eventually taking it into creating a pull request that adds their dependency into event stream as event stream own dependency tree. So supposedly this is supposed to be something that is very genuine to the code base for event stream, except that they really own that dependency, so they were the maintainer of the dependency that was added. And realistically, what happened a couple of weeks further, they added a code payload to their own dependency that is now part of event stream that injects malware into a specific Bitcoin wallet application. So they have surgically understood what is needed to be done to add that kind of malware. They have done essentially a mastery of OSINT, of open source intelligence, reconnaissance to target specific open source developers of that wallet application. And basically this whole thing had gone unnoticed for almost 3 months and ended with 2 versions released from this Bitcoin application with the malware being included. So this is all happening, a very significant, in my opinion, security incident in the NPM ecosystem, real story. I suggest reading more of the details. And again, part of something that is considered a major thing, especially since event stream gets millions of downloads a week, and it is part of powering a lot of core libraries in the ecosystem itself. And so more on these risks, right? With this open source registry as big as NPM, many risks lure us. One of which is that some popular packages reach more than 100,000 other packages via direct or indirect dependencies. And so this means that there's an amount of packages that could reach a whole lot of users through just direct or indirect being included in a project by other dependencies. So as a point of reference here, event stream that we just talked about was probably the most significant and severe incident, in my opinion, that we witnessed on NPM. And yet it did not even, it only compromised something like 5,000 packages. So it's not even making that top 10 that we just talked about in terms of reaching 100,000 packages. And yet it was a very severe incident on the ecosystem. So more on this, right? This research paper pointed out another interesting fact, and that is if we do an average NPM install for a user, you'd be introducing 4 levels deep of nested dependencies, basically showing just how much we depend on open source software, right? That is you can see on the side as well the differences with PyPI versus NPM. So there's a whole ecosystem in play here and useful ways behind how we manage open source packages, but as an ecosystem, as a way of how developers work between PyPI, for example, and NPM, things are still very different. That is okay. And so let's take a mental model for a second, which I want to share with you. Let's imagine the what happens. And so imagine having this mental model of this whole app that you're building, right? You're building code, you're writing it, you're deploying it somewhere. Your mental image of that application you built is this whole kind of round blob thing that you go off and ship. Except the reality is a bit different, right? This mental image of all of that is a bit wrong, because the code that we actually write is significantly smaller, and there are a lot of research papers around this, and reports from like Gartner's and so on about the fact that open source makes a lot of the app, right? It makes maybe 90%, maybe more, maybe less in single-digit kind of percentages. But that is it, right? If you're building an app that's mostly going to be powered by open source, that is great, that is amazing. We're leveraging a beautiful open source world to boost our productivity. Need to also take into account what exactly this means. As we dive deeper into this, it's hard, as we said, to imagine writing software without relying on any open source dependencies, but managing dependencies is a task. It's a very challenging one on its own. And so it requires due diligence. It requires you correctly keeping up on track of the libraries that you actually use, as actually they power your application in a sense. And so the thing is that now it's interesting to see where are we getting most of the vulnerabilities from. And this is from Snyk's latest State of Open Source Security from 2020, where we looked at the data that our users, using Snyk, actually using. And so what we can see is it differs again from ecosystems, but mostly if we focus on this NPM, RubyGems, Maven central ecosystems, we can see most of the vulnerabilities that we find for users that we tell them that they have a vulnerability in their projects, they actually appear in those indirect dependencies. So that means even if you're tracking all of the newsletters and updates and the repository updates and commits on a major framework like that is used as a direct dependency, like Spring or like Express or like Angular, so all of those kind of like big projects, that is great. That is a great mindset, very security aware and so on. That is amazing. Don't stop doing that. But it means that most of the time where we'll find vulnerabilities in the project for you, it will not be in specifically in Express. It will be in the dependencies that Express as a web application framework for Node pulls in by itself, right? And it pulls in quite a lot of them. And so this is just as an example, right? Express or something else, not to say that these are insecure, but we're saying dependencies, bring in with them more dependencies, and that's where usually the trouble happen in terms of security issues, mostly on those kind of ecosystems. So, indirect dependencies are those that we kind of have less control of, but mostly unaware of. They pose a risk. Let's look at a different kind of vulnerabilities beyond, the regular CVEs and so on of, the OWASP top 10 and so on. And so I pulled in this table timeline of malicious attempts that were happening on several incidents on the NPM ecosystem with some packages. Some of you, you may know, for example, event stream we already talked about in this session. And I want to focus on one of them, and really ask, what can possibly go wrong with indirect dependencies. So let's look at what's happening, and I'll focus specifically on get cookies, as it's an interesting one. I like this one. And so it sounds like it makes sense, right? Get cookies, you install this to parse HTTP headers cookie data for your app. But does it actually do that? Or what else is it actually doing there? So in fact, get cookies is nothing less than a command and control backdoor that allows anyone who have installed it, allows anyone with knowing the intention to use it to be able to execute remote command on any web server that has it. So this is what it does, right? You may have wanted to install get cookies for one thing, but actually it does something else behind the scenes that you may have not known about. And all of these are real stories from the ecosystem. This is roughly 40 lines of code of payload of malware that get cookies had inside it. I've cut it down to the most minimal and the gist of it here. And so you can see that it actually has 3 commands, right? There's a switch case, just a few lines above it, it actually tries to parse the data from request headers. So anything you pass as a request header, it tries to parse it in. It tries to take the data from that, and those make up 3 commands basically. One of them says reset the buffer, or rather, allocate data into the buffer, right? And then the other one says, load data into the buffer. Once the data is loaded into the buffer, then the last command helps us to basically execute whatever is on the buffer. And so whatever gets on the buffer is actually JavaScript code. So I can send on the wire, if a web server uses this and doesn't even have, I can access this route without any authentication, any login, anything. I'm basically able to manipulate and send whatever JavaScript code I want, and then evaluate it on runtime when the server runs. This is a real thing. This is what happened. Here's an example of simplifying this. So I'm sending this X secret header. I'm hiding this command inside it between this G and an H, and there's a whole command palette that I need to add my payload into. After that, I can send this JS code, which whatever I want to basically do on the server. And lastly, I can send this command over the wire, which says execute whatever is on the buffer. This is it. This is the payload. This is how you would run any command on a web server using this get cookies malicious package. This is interesting, but the thing is, it's not enough. It's not enough in an ecosystem that has 1.4 million dependencies. How do I get users to use get cookies and not something else? Because there's obviously other ways, other cookie parser packages. And so to begin with, first of all, whoever these attackers were, they have hid get cookies behind this pyramid of other nested packages, basically because, when I install a package, it may include, like we just said from the research paper, right? It may include several nested levels of dependencies that I'm using, but I'm probably as a developer not going to go for every package and check what it added and then code review it and so on. So this is one way of hiding, whatever is you're doing, just add it as a dependency. Going to be a very minimal chance that someone is actually going to review one by one. And so this is one thing that they started doing, but still, if HTTP fetch cookies looks okay and sounds okay for a developer, if you search for it and you want to use it as, in your project, it is still probably very low count downloads, for this package, and so it doesn't really convey any real confidence for a person. What if we were able to compromise another package, say mail parser, which invites something like 500,000 downloads a month, and then make HTTP fetch cookies a dependency of that? In return, what would happen? Mail parser itself is probably not going to be exploited in terms of what happens here with cookies, because that is not the purpose of mail parser per se. But every download of mail parser from this moment on will actually increment downloads of all of that chain of nested dependencies. And so we are gaining trust by doing this. Question is, how hard would it be to compromise mail parser? Well, apparently that happened. And so mail parser was indeed compromised. This whole story indeed happened. And these are the troubles, the insecurities that we are dealing with open source need to be aware of. So maybe one point of thing to take from an observation to take here, right? It's kind of like, the sad realization that, added complexity for developers, security by code review has to be on point, right? All the time. We have to be on point all the time. Attackers only need to get lucky once. That one time to add, a dependency, a vulnerability, something that we haven't really noticed. And the thing is, it does really happen all the time. Mail parser being compromised is just, one form of malicious packages, or different forms of malicious packages. For example, like what we're showing here with Webpack CLI requests, like these typo squatting attacks that are happening on different registries. By the way, this is not really only for NPM. It's just showing that with this screenshot, but we actually seen typo squatting attacks happening on RubyGems and on Python, and so NPM is not really unique in this space, but it's happening all the time. And so this is where also supply chain security concerns are a lot wider, right? They're encompassing different ecosystems. We need a way to deal with them, and so on. What about a security blind spot of Lockfile attack vectors? Lockfile are a good way in terms of open source dependencies to lock them in, right? That's where the naming comes from. And the idea of pinning down the versions of the dependencies that you use in order to have deterministic builds and repeatable builds and all of that. And so it is very common to in various ecosystems to have log files. Specifically in NPM here, what we're showing is I've made an update. You can see the pull request here for a project in GitHub. I've made an update to one of the dependencies, really minor updates for this REST API from 0.2 to 0.4, a patch version, very minimal. It's not even my code, right? I'm upgrading some other dependency that the project has. So overall, seems very legitimate, and even myself as a maintainer, I'd probably just go ahead and merge it in. That's fine. Except there is something here that is happening behind the scene that we may have not noticed, and that is if you look a bit down to the PR itself with a file change, you could see the yarn log file, but it's not really showing the entire diff because the log files are usually machine generated. They're not supposed to be human readable, and they're not supposed to be edited and modified and handled by a human. It is something that the package manager takes care of in terms of having integrity hashes and so on. And so, GitHub being GitHub as a platform, just showing us, just like 500 lines of code to review. It's kind of like cropping it up. Doesn't really open it up for us to review easily. Except if we open it up, let me show you what's going on. I've actually, when I made this PR to that project, I've actually changed. If you look at in the middle of the screen, the most significant part of the change, it's changing this MS dependency from being served from npm.js as the ecosystem, right, as the registry, the official registry to take it, into being served from my own GitHub fork of MS, right? It's github.com/lirantal/ms, and it has this whole master tag that it can take, the release tag that it can actually take, they can use it. And package managers, they do support getting packages and installing them from different resources. Things like using them from GitHub repositories, things like using them from file system, things like using them and importing packages from even GitHub gists, right? They can even be imported using that way. And this is where this is the blind spot that Lockfile has. If you are not having and mandating security policies around the Lockfile and what is allowed as a trusted source, if you just merge this, what would happen is the project will actually introduce this new MS dependency with my modified version of it into the project. As the maintainers may start using it, what would happen is I actually did something, in that experiment, very naive, just to prove the point, or having a post install script, which packages usually have as well, and allowing the npm package manager or some other package manager to execute those any arbitrary code that is mandated to be executed by the dependency. So this is really a really naive experiment, but showing the extent of what would happen as an impact. If you want to learn more about this, it's a lot of this on the Snyk blog. I wrote a tool to lint it, so you can look at what is going on there and have better security policies around all of those log files security issues. So this brings us into a lot of now a lot of open source and maintainers and what is going on there in a lot more sense. And as you can see, we're actually transitioning a lot more from just speaking about open source security as a whole to growth in ecosystems, to dependencies, to malicious packages, to supply chain security. I'm going to take it over to even more deeper into this state of how maintainers are part of this ecosystem. There's a lot of load on maintainers themselves, and mostly on open source people are doing this in a more of like a volunteer kind of way. And so one of the things I wanted to highlight here is in last year's GitHub State of October's report, they have mentioned, they have highlighted, to be exact, that security was the most popular project integration app category. So the more we use open source software, the more risk accumulates, obviously, as we're including someone else's code into our own code base and could introduce, now or future vulnerabilities. And so having automated tools to help us, alleviate this, I think, rigorous manual code review and tests that run fast for those critical CI/CD adoptions that we want to have, it's something that needs to be at the factor, right? This needs to be a way that we are able to move fast without breaking things, moving fast and moving securely. So there's a lot here, but now diving a little deeper into it. Now let's talk about maintainers, right? Understanding the impact of security fixes as they roll to us as users, but they roll to us from maintainers. And so when maintainers eventually get to fix a security issue and release a fixed version, understanding what kind of decisions they're making, or maybe helping them making the right decision, is actually really, really important, because it ensures that we as consumers are able to remediate this vulnerability. Let me give an example of what really happened from a story. I took a couple of screenshots here from something I looked at, and was really interesting to share this, because this is an open source package which someone just chimed in and said, no, there's a man-in-the-middle attack vulnerability in this project. It was reported by Snyk here and there. And you can see the maintainers, everyone kind of like voting up, let's remediate it, let's fix it, and let's issue a fix for it, right? Except what happened is, all with good intent and all with really positive work here in terms of collaboration, but the maintainers, did get involved to publish it and publish a new release. However, the release that they published was actually a major version change. So, if the vulnerable version was a 2 point something, a new version being a 3 point something, a major version release, now has different impact on users. Because if I'm upgrading from a 2.1 to a 2.2 or something like that, that's a minor version or maybe a patch version. As a developer, I know it will probably have less chances of breaking something just because of the semantic versioning contract saying I only upgraded a patch or the minor because it's a bug fix or it's a small feature, it's backwards compatible and so on. But the moment that you introduce a security change as a major version, as a jump from a 2.x to a 3.x, as a developer, I may not know what else you did, or maybe an API contract was broken because you needed to fix something and so on. And that would entail that for me as a developer, I will be more hesitant and more careful and cautious when I need to merge and get this fix. Except this is a really fix I want to get. This is a security fix I want to get as fast as possible, not as slow as possible. So understanding how this impacts maintainers and how it's kind of like it's a zero-sum game, right? We're all part of this open source ecosystem in a perspective, and so we need to do better at this in different and multiple levels. And so far I've been talking about security risks and malicious packages in different ways, but there are regular security vulnerabilities in a sense, right? Regular in a sense, just CVEs of things from like OWASP top 10, not even supply chain attacks or malicious packages or compromised of packages and so on. Like this one, for example, Markdown to JS6. It's an XSS vulnerability, is still at the top no matter what year it is. XSS is going to be at the top. And while developers rely on modern front-end JavaScript frameworks like React and Vue and others, they may not realize that the security issues lies in the dependencies that they add to their projects. So while I'm as a developer using, for example, React, and this is supposed to be a React helper dependency, if I'm using React, I may be using all the security best practices from the framework, and that's amazing. That's great for me as a developer. Except when I'm adding a dependency, that dependency may not be using all those best practices. It's not really scalable for me to go in and check and code review every change, every update, every code of that dependency that I add. The whole point of using dependencies is, we can build together and build better things. So not understanding that, I think that is also a mental image that we need to be better at. And this is the importance of also doing better in the front end in terms of finding security vulnerabilities in packages and remediating them without having this bias of saying, my front-end framework is fine, is secure, but actually dependencies could make it insecure in a sense. This is all super important to understand. And so what I want to take this even further into like a global kind of like impact of open source is, this is not just impacting dependencies of language-based ecosystems like like Java, like NPM, like Python. This is actually a lot more than that, because open source is very encompassing. And so container security is part of it too, right? The growth of open source software is impacting container images as a whole. And so, the adoption of application container technology is increasing every day. It's already at a remarkable rate. It's going to grow more and more as it is probably easier for us to manage software in this way. The reports around the usage is 1 billion weekly downloads of container images, more than 1 million new applications added into Docker Hub over the last year. And so this is really big. And this is not advocating for container technology here, but I'm saying this is something that we all use. And let's look at what's going on there. So that State of Open Source Security looked at that report looked at Docker images, the top 10 Docker images, and what we're finding is, Docker images almost always bring with them vulnerabilities alongside their great value, and that means, these findings, these are the top 10 most popular Docker images on Docker Hub, but you can see that by default they all kind of, except for that Ubuntu on the far right, except for that, everything here ships off with at least 30 security vulnerabilities by default. So if you were starting a project, having your Docker file having from Node latest or Postgres or Nginx or anything else here, you'd be pulling in tens, maybe hundreds of vulnerabilities just by using the image itself. And it's actually super interesting because most where vulnerabilities actually get introduced. And so most vulnerabilities actually originate in the base image that you select, right? This is the the from clause on the Docker file. But here it's actually crucial to understand, like with open source dependencies, how exactly that happened. It's actually also crucial to understand with Docker images, which base image is that parent image is actually based on. So for example, if I was using just Jesse as a Debian Linux OS for my Docker image, I'd be pulling in almost 700 vulnerabilities just like that. But if I would make more of a conscious choice to pull in something from Ubuntu, like what's there, like Xenial or Bionic, or maybe a different distribution of Debian, maybe Seed or Buster, I'd be pulling in less vulnerabilities. So this is actually understanding which image to pull that has less of them. Not saying that this is the way that you should just figure out what you should use, but this is giving us an understanding of what is going on. Now, Snyk has done, just like with open source packages, has done a bit of a research to the users, using Snyk to find security issues in their containers. And we've looked at what happens there and how we can help users. And so one thing we realized really quick, and this is an astonishing input, as far as I'm concerned, this is the fact that 44% of Docker image vulnerabilities can be fixed if you just use a newer base image. So it's essentially saying fixing is really easy, right? It can be easy if you're aware of what base image you're using, and then knowing that you need to swap it with something else. But this is the tricky part in most cases. This is, if you're using container security tooling, you may, whatever suits you, you may get reports of, just like Snyk showing here, 862 vulnerabilities detected in the container. That's great. That's a really good starting point for any security tool. But this is also the point where most security tooling stops. And what the developer now, for me as a developer owning a Docker file, what I need to live with at this point is, what exactly should I move to? What exactly should I change? I have no idea. You told me I have 800 vulnerabilities. That's great. But what do I do at this point to be better at it? And this is where, for example, Snyk would help you and say, there are alternative base images, based on what you're using, right? Your current image pulls in 862. If you want to do an alternative upgrade, like, this is more of a major change, you can reduce this to 54. But even if you do a minor upgrade or a different kind of upgrade, you can reduce that 800 to 600 or 500 or even lower as 54. But now the choice is made for a developer to make it more of a conscious one. And so this is where container security tooling, evolves and will evolve more into things like infrastructure as code and misconfiguration, and helping developers figure out what could get wrong and what they should probably do to drive them into an action they can actually remediate the problem. So let's get back to CVEs. Who remembers what this CVE stands for? CVE 2017. That's gonna be a story from 2017, right? So this is actually the Apache struts2, right? It's an arbitrary command execution impacting Apache struts2, which, it happens by, the exploit itself happens by someone sending a crafted request with specific payload into the content type header. And, the gist of it is basically a proof of concept was made public shortly after this CV was disclosed, demonstrating this vulnerability. But it really wasn't, soon enough, I guess, before this Strut servers all around the world were getting exploited in the wild by this proof of concepts. One of them was Equifax's servers. So no authentication is needed if you can run that request to the server. This is just impacting the web server itself. And so this is a lot as a story. And estimated losses for Equifax are around $1 billion mark. For a vulnerability that was really just one pull request away from being mitigated, right? If you had a tooling that would surface the issue, there's a vulnerability here, there's a CVE. Here is the pull request that upgrades your POM file with the latest version of struts to remediate this. So developers would be empowered to take security ownership and remediate this vulnerability. That's on its own is amazing, right? But what if they're not? What if they're not empowered to do that? So this kind of vulnerabilities live in production until someone finds the quickest way to mitigate them and prioritize and make still developers part of this as they need to roll an upgrade and an update to the app itself. So I've talked a lot about open source dependencies. Before we conclude, I kind of want to say, these are open source dependencies that have a lot of security risk in different ways. But how do they actually make it into the app itself? How do they manifest as a vulnerability that impact an app? And that may not be a direct line that a lot of people can draw. And that's where I want to do a demo and share with you an example of what exactly that means. So this is a part where I shift into this hands-on demo. I'm gonna maximize the visuals as much as I can if anyone is watching this on smaller devices or remote screen. But basically what we have here is an app. It's a to-do app, iSans, and we can do more here. I actually have an about page, which if I would go to, for example, here, would render some kind of data. Now this app is entirely JavaScript, Node on the front end, Node on the back end. And the way that I'm registering and I'm registering a template here to generate this kind of view for the app is using a package called Dust. So Dust is a very popular package by LinkedIn. It gets some tens of thousands of downloads a week or so. It's used as a template engine. There are different options, in the ecosystem as you'd expect with NPM. So I'm using this, and so this is my, this is the part where things get interesting, right? This is my view. You can say I have a condition on a device, and then based on the device, I may render the view in a different way. So this is to say, if I were going here and adding this device equals desktop, I might get it, the view itself rendered in a smaller font, whereas if I'm on mobile, I'd be getting it in a bigger font. So this is nice, this is great, but Dust has apparently a vulnerability. It has this specific version, right? It has a vulnerability around allowing arbitrary code injection. But how exactly does that impact the app itself? How could you inject something here? We can think about several ways of doing this. I mean, we are trying to, there's an if condition here that we're trying to figure out if there's an equality. And so you can imagine me maybe trying to add maybe a single quote to this side or to the other side, or something here to kind of add user control the input from the user, and maybe terminate the string and do something different around it. So if that doesn't work, you can see the debug data from the app itself. It's just showing us as a debug what we're sending, but not really doing anything here. And we can see it here as well. The interesting part around Dust that we should probably mention is Dust as a library actually has some good measures inside it to control the input and escape it, to basically mitigate those kind of like script injections. One of them is this. It has this escape HTML function, which checks if the type of whatever was sent is a string. If it does, run some more checks, and if needed, it will go in and replace whatever we sent with the HTML entity equivalent. So trying to sanitize, or properly saying escaping, the vulnerable or malicious code into something else that wouldn't really do anything, and then return it and so on. Except this is really happening only if something is a string. If it's not a string, this whatever variable is returned as is. But how can we make it not a string, not going through this one stance of code, yet impacting the app? So this is where things get a bit more complicated, and this is where attackers actually, chain the attack in different ways. So if you were able to go ahead and say, well, the device is actually an array, right? And I may have several devices. It looks like it's still working fine. In terms of the app is still working, even if I'm telling the servers, maybe this is an array that you should expect. But this is not really the case. The moment that I try to add a single quote here, things break, and things break in a way that also share more information on me and in terms of the app itself, right? How I build the app, what is going on, why exactly did it break, and I can see it here as well. And so let's look at a practical example of how would I exploit it. And so to understand more, and this is all open source, right? I could go to the source code of Dust, study it, understand what are the security vulnerabilities, and wrap my my way of exploiting it around it. And so we can see that this is the if function. This is the helper for Dust that we're using here. You see the if function is sending a condition variable. And so that condition actually takes part here. We're actually using eval, which in JavaScript evaluates code on runtime. And whatever is sent as a string is evaluated as a valid JavaScript code. If it's not valid, it will throw something like what happened before. So now that I know what is going on, and maybe I get an understanding of what is going on here in terms of the logic, I can go and try something like this. I can go and say, first of all, this is just a simple request that I'm sending off, and I'm just to show you that this works. But then I can go and say, well, this is an array, and I'll go and close this mobile thing, add a function call, just to console log, and I'll close it with another single quote. So effectively what this means is, you could imagine that basically I'm doing something like that. This is my input, console log, and then I'm adding this one to conclude it. So my payload is basically trying to conclude a string so that the string is working fine, because I need to close and open it. And then in the middle of it, I'm trying to run a function. In this case, it's just a console log. So I'd expect something to happen on the server when I send it. And the moment that I do, I can see that console log 1 now getting processed by this backend Node server. And what I was essentially doing at this point is running any arbitrary code injection that I wanted on the backend. So I could run something like require child process and do something with child process and spawn it and read file system data, whatever I wanted to do. And so this is the case where the dependencies have vulnerabilities, and they have real impact on application vulnerabilities. It may not be all the time, but you just don't really want to take that risk, right? And so this is where remediating and doing it well, and doing it with tooling that helps you do it well, is super important. So who should be responsible for security, right? After all of this session, all of this talk, I hope I inspired you to understand that, it's obviously a shared job. We all work together towards creating quality software. That means it is performant, it is accessible, it is secure as well. We've run that State of Open Source Security report. It has a lot of interesting insights. One of them showing across software and across infrastructure, the fact that developers see themselves as pretty much a good owner in terms of they care for the security of their app, which is great. This is what we want to do. We want to empower them and make it easier for them as much as we can to take that into account and indeed secure their app. That could be through different ways. That could be, for example, helping them with this like security integration under CI, saying, all the tests are great, you've deployed into a staging website, accessibility end-to-end, everything is okay, but we've detected some packages that may introduce vulnerabilities into your version. I'm going to stop the build until you can remediate it. In a better way. You don't want to just gate it, right? So this tooling also helps you and say, even beyond just the CI that is now running, and maybe there's someone rushing there to production, in parallel, what we'll be doing is let's open a pull request to the developers, tell them, there's a high confidence in merging this dependency upgrade to fix the vulnerable version. They can go into the PR, see it, understand, read the change log and the commits, and understand that this is an okay change, and then merge it, right? This is what we're trying to do and help developers, build fast, right, and stay secure still. So this is all for me. I want to say, open source is awesome. Please enjoy responsibly, whether you're doing any language ecosystems or container or anything else with open source. Thank you for staying for my talk. I'll go ahead and answer any questions now. So if you haven't added any questions so far into the box, you're welcome to do it, and I'll be happy to go through them. And over to you.
All right. Yeah, thanks for that great presentation. We do have a question ready for the Q&A. However, as Liran said, if anyone has a question for him, please put it into the questions window now. This question asks, won't a good SaaS tool catch these vulnerabilities within JavaScript code?
It's a good question, I guess, right? What makes a good SaaS tool? So SaaS is, it's used usually for your own code, right? And we're talking about more the software composition analysis here, where you'd actually try to review what is going on third-party dependencies. So you usually wouldn't run SaaS tools on the dependencies, but your own code. So I think there's probably a difference in terms of when you would use the different tools. And also, there's a difference there between how do we find about the vulnerabilities. So vulnerabilities in your own code, it's usually something you'd have to look for, right? You'd have to do a security code review or run a SaaS tool and find out about it, which is, just fine. On third-party libraries, there's, usually there's no one person that goes through and code reviews all of them to find something, but rather they are known and publicly known vulnerabilities, right? That everyone is made aware of them the point there's a CVE. So I guess there's a difference there also in terms of not only when you would use it, but what is the impact at that point, because that is now a known vulnerability that an attacker may know about. A vulnerability in Express app gets downloaded 50 million times a week. Now there are 50 million potentially vulnerable users of Express if they didn't upgrade that would be susceptible to this kind of vulnerability. That's maybe to say you should probably use both SAST and software composition analysis.
All right, that's all the questions I am seeing submitted. Oh, one just popped in. The biggest hurdle my team is currently grappling with is how to scan packaged Java code, for example, jar files. What if a vulnerability requires multiple jar files to complete the vulnerability, as you demoed and mentioned?
Right. It's a good question. I don't have a great answer on that one. I definitely encourage maybe pinging me over on Twitter. We can maybe connect afterwards, and I could probably hook you up with people more experienced on the Java side. But generally speaking, if there's only a way to just do a chained attack in terms of probably putting together multiple dependencies in your path to exploit something, that is something that you'd probably only know about if there's a vulnerability for each of them in separate, right? If there's a vulnerability report for each of them in separate, and then you would probably need to upgrade each separately. I haven't seen a case in which there's a vulnerability impacting you because of another library being vulnerable. So not to say that that doesn't exist, probably does, definitely does. But I haven't seen that being a very a major case around.
All right, thanks. How is Snyk different than Dependabot in GitHub? Dependabot warns for security issues in my GitHub repos.
Right, so there's some differences there. I think probably going into the website and reaching out would probably be able to give you more details. But generally speaking, you could probably segregate the differences into different categories. One of them is the database richness. So what is the database that, of vulnerabilities that you're building upon and then opening these pull request fixes? And so for Snyk, it's something that is super rich. Of course, I'm advocating for that, so might be a little biased. But honestly, if you do the comparison and you try several projects from experiment, I've done some of that around, for example, Angular. Whereas for Angular, there's like 24, 27 vulnerabilities, but only a few of them have CVEs. I think maybe a couple of them have actual CVEs. And so when you depend only on CVEs and maybe some other databases, but lower in terms of reach, you'd only find a few vulnerabilities to upgrade and offer fixes. Whereas if you use something like Snyk, for example, which has a lot of reach in terms of the database itself, the underlying database that powers the tool, you'll get a lot more security fixes proposed, as you will know about a lot more vulnerabilities happening. So yeah, that's definitely, sorry about that. That's definitely one. The other one is the capability inside. Dependabot and Snyk do differ in terms of how they work for Java and for Node. So for example, if you have a Node project that doesn't have log files, what will actually happen at that point? Because Dependabot relies a lot in what it does with log files, and also it does things differently the way that Snyk does. And so Snyk will actually build a whole dependency tree of everything you have, whereas with Dependabot, it might happen in a different way. For Java, for example, if you use Dependabot, it doesn't even do the whole transitive tree of dependencies, but rather just the direct dependencies. So there are definitely different ways. Use whatever tools work for you. If you want to look into more of why the Snyk stuff, reach out and we'll be happy to help.
All right, that's all the questions we have for today. Liran, do you have any closing thoughts you'd like to share?
No, I mean, just use open source securely. That's it. That's it. Reach me out if you have any questions. I'll be happy to help.
All right, well, thank you so much, Liran, for your great presentation, and to Snyk for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.